Okay, picture this. Imagine a kid opening a birthday present, pulling out a brand new Spider-Man suit and immediately running straight at the living room wall, fully expecting to just scurry right up it. Now, normally they'd just bounce right off, right? But the crazy thing is, according to scientists, this kid isn't actually that far off. In today's Explainer, we're going to see how scaling walls like a superhero might, very literally, soon be child's play. But wait, it's not just superhero suits we're talking about here. We're talking about engineering cables strong enough to stretch all the way from the Earth to the moon for actual space elevators. We're talking about building literal cars out of molecules and even regrowing human limbs the exact same way a lizard regrows their tail. These wild sci-fi dreams are getting closer to reality every single day, and it's all thanks to one absolutely awe-inspiring field: nanotechnology. So, before we really get into the weeds, we have to wrap our heads around the scale. What exactly is a nanometer? Well, by definition, it's 1/1000th of a meter. Think about the width of just 4 silicon atoms sitting side by side. Actually, to truly grasp this mind-boggling scale, think of the size difference between the entire planet Earth and a single orange. That massive, unbelievable difference, that is the exact ratio of our normal, macro world to the nano world. Let's break this down a bit more so you can see how it builds. Imagine the eye of a sewing needle, which is about 1 millimeter wide. Tiny, right? Okay, shrink that down 100 times, and you get the width of a single human hair. Now shrink that down another 100 times, and you've got a red blood cell. Keep going. Shrink that down even further to the measles virus, which is about 300 nanometers. A true nanoparticle is actually 3 times smaller than that tiny measles virus. That's the completely invisible world we're exploring today. Here's our roadmap for today's Explainer, breaking this giant topic into 5 clear stages. First, the dimensions of the infinitely small world. Second, the nanotechnology of nature. Third, milestones of human discovery. Fourth, miracle materials and nanomedicine. And finally, quantum physics and unknown risks. All right, part 1, dimensions of the infinitely small world. We're actually going to begin our journey in a realm humans interacted with long before they even knew it existed. You've got to hear about the Lycurgus cup. It's this 4th century glass chalice sitting in the British Museum right now. Way back then, 4th century Romans unknowingly used liquid gold and silver nanoparticles, mixing them right into the glass. This alchemy gave the chalice a totally magical property. It literally changes color depending on how the light hits it. They had absolutely no clue why it worked, but today we know those gold and silver nanoparticles were interacting with light on a microscopic level. It's just wild. Which brings us to part 2, the nanotechnology of nature. Because long before Roman glassmakers stumbled onto it, nature was the original master of this scale.
Just look at the stark contrast out there in the animal kingdom. Take the gaboon viper. It hides in the leaves using these crazy nanoreliefs on its dark scales. These microscopic structures act kind of like a dense coral reef, trapping and absorbing light so perfectly that the snake becomes impossibly black and practically invisible. Now, on the total flip side, you have the panther chameleon doing the exact opposite. It actively changes the spacing of nanocrystals in its skin using its nervous system. This reflects different wavelengths of light, putting on this brilliant, colorful carnival suit depending on its mood.
And get this, we're already copying these natural superpowers. Imagine never ever having to wash your jacket again. We've created completely waterproof, self-cleaning textiles inspired by the lotus leaf, which uses microscopic wax bumps to force water to bead up and roll right off. And hey, remember that Spider-Man suit we talked about earlier? Scientists are studying gecko feet, which use millions of tiny nanofibers to grip basically any surface. By mixing polyurethane nanofibers and carbon nanotubes, we are actively developing sticky climbing robots and adhesive bandages that don't even need any glue.
Moving right along to part 3, milestones of human discovery. This is all about how scientists finally learned to see and manipulate this invisible world for ourselves. So the real turning point here is 1981. Before then, Richard Feynman had theorized about the nanoscale and Norio Taniguchi gave it the name nanotechnology. But in 1981, 2 physicists, Binnig and Rohrer, invented the scanning tunneling microscope. This thing didn't use light. Instead, it used a quantum effect to actually feel the shape of individual atoms with an ultrafine electrical tip, kind of like reading Braille. This won them the Nobel Prize and finally let us see the building blocks of matter. Shortly after, scientists began discovering entirely new artificial structures, leading right up to a massive breakthrough in 1991.
That ability to manipulate matter gave us the carbon nanotube. Discovered by Sumio Iijima, it's basically a hollow tube made of a hexagonal lattice of carbon atoms. It's less than a nanometer in diameter, but it is an absolute wonder material. I mean, it's harder than diamond and remarkably 6 times lighter than steel. It's so strong that, theoretically, you could have 100,000 people pull on either side of a single nanotube without it breaking. 100,000 people. Plus, because its structure is so flawless, electrons just cruise right through it without colliding, giving it perfect electrical conductivity with zero heat loss. All right, on to part 4, miracle materials and nanomedicine, because things get very weird very fast when you shrink them down to this level. To really get why nanomaterials act so strangely, picture a Rubik's Cube. Now, imagine breaking it completely apart into all its tiny individual blocks. You still have the exact same total volume of plastic, right? But suddenly, you've exposed vastly more surface area to the outside world. All those uncolored inside faces are now on the outside. The direct consequence of all that extra surface area is just fascinating. In a normal-sized piece of material, most atoms are cozy on the inside, fully bonded to their neighbors. But with nanoparticles, almost all their atoms are on the surface, practically begging to bond with anything nearby. Their chemical reactivity just skyrockets. This is exactly how self-cleaning windows work. They're coated in titanium dioxide nanoparticles, and when UV sunlight hits them, that highly reactive surface reacts with oxygen and literally destroys organic dirt and pollution right there on the glass. And let me tell you, this reactivity is a total game changer for medicine. Think about traditional chemotherapy. It's kind of a shotgun approach where maybe 1 in 100,000 particles actually hits a tumor, and the rest just poison healthy cells. But with nanotechnology, we can pack medicine into a stealthy nanocarrier. It sneaks right past the body's defenses, binds specifically to cancer cells, and drops the payload exactly where it's needed. Or even crazier, scientists are sending iron oxide nanoparticles directly into tumors, then turning on a magnetic field outside the body. The nanoiron heats up and destroys the cancer from the inside out. No collateral damage. The breakthroughs here are mind-blowing. Researchers have actually restored sight to blind mice. Yeah, they implanted titanium nanowires coated in gold nanoparticles directly into the mice's retinas. These nanowires acted just like natural photoreceptors, turning light into electrical signals for the optic nerve. And on top of that, chemists are building molecular machines right now. Actual tiny nanocars with a chassis and wheels powered by light that can self-assemble. Just imagine a future where you go in for major surgery and there isn't a single incision. It's just swarms of these tiny machines repairing you from the inside.
Finally, part 5, quantum physics and unknown risks. Because before we go ordering our self-cleaning toothpaste, we really need to talk about the massive unknowns of this uncharted territory. See, at the nanoscale, the standard physics rulebook completely goes out the window. Gravity, it basically stops mattering. If you pour water in our world, it flattens out. At the nanoscale, it balls up into perfect spheres. And if you throw a tennis ball at a brick wall, it bounces back. But in the quantum nanoworld, particles act like waves. Sometimes they bounce back, and sometimes, through this wild process called quantum tunneling, they can literally just pass right through solid walls.
And honestly, that is precisely the danger. We've engineered these highly reactive, invisible materials that can slip through virtually any biological barrier. They can pass straight into human cells or travel deep into complex ecosystems. And the thing is, they're already here. They're in our cosmetics, our clothes, our building materials, sometimes even our food. Yet the long-term consequences of these particles building up inside our bodies or our environment, we have absolutely no idea. We are playing with a reality-bending technology that is barely 50 years old. Which leaves us with a pretty heavy question to ponder as we wrap up today's explainer. As we gain this unbelievable power to reshape the universe atom by atom, designing materials that totally defy biological limits and classical physics, what are we doing? Are we stepping into the role of godlike creators, completely in control of our destiny? Or are we just sorcerers' apprentices messing around with invisible forces that we don't truly understand yet? It's a fascinating and maybe just a little terrifying thought to carry with you.